In this video, we're going to be talking about how to use standard deviation along with the mean to better describe a distribution or to understand it. And more specifically in this video, we're going to talk about Tchebychev's theorem. And so here we have a data set, 50 people that were randomly selected. We're asked how many siblings they had, and here are 50 data points, and I already created a histogram for that. And so I'm going to recap really quickly how to find the mean and standard deviation using our built-in formulas. We have, in this case, the original data, so I can just use my built-in formulas. So for the mean, I use the average formula. For the standard deviation, since this is a sample, this is definitely not everybody who has a sibling, we're going to use stdev.s. And then just for reinforcement's sake, let's find the median. All right. So in this example, our mean is larger than our median, so we would expect our distribution to be skewed right. That's just a clue to what the distribution would be, just based on the mean and the median. However, in the previous class, I think we saw, or a previous video, we saw a data set where the mean was slightly smaller than the median, and yet it still looked like a skewed right distribution. And that's okay too. So this is just painting one picture of what the data set might look like. We look at the histogram. This paints another picture for what the data set looks like. And so this is definitely skewed right. Looking at the tail, this is a very pronounced tail going off to the right, and most of our data is off to the left. So I'm saying skewed right. And the mean and the median just reinforce that idea. Okay. Now, because I know the standard deviation going along with the mean, this standard deviation is very big, which in the previous video I said if it's not at least 1/3, if it's not smaller than 1/3 the mean, then the mean's probably not a great indicator of the measure of center, and our data set's probably really spread out. That's still true. But I can use this standard deviation to tell me more about this data set if we follow Tchebychev's theorem here. And what Tchebychev says is that for any distribution of data, no matter what the shape is, the percentage of data that falls within k standard deviations of the mean is given by 1 minus 1 over k squared, where k is an integer that's greater than 1. So according to Tchebychev's theorem, I don't know anything about how much data should be within 1 standard deviation of the mean. But I do know that within 2 standard deviations of the mean, I should have about 75% of my data. Okay? Now let's just double check and make sure that this formula was created properly. I'm going to put an extra set of parentheses right here so that I know that it's 1 minus 1/4, but I know that's definitely 0.75. If we were 3 standard deviations away from the mean, this would be 1 minus 1 over 3 squared, which gives me about 89%. If we were 4 standard deviations from the mean, this would be 1 minus 1 over, parentheses, 1 divided by 4 squared, which gives us about 94% of our data is within 4 standard deviations of the mean. Okay, so that's what Tchebychev's theorem says, and we can keep going to 5, 6, 7, 8, however many standard deviations you want to go. Because it's 1 minus 1 over k, this will never actually get to 100% of the data falling within a certain number of standard deviations, but it's going to get closer and closer. The other thing to note here is that it's at least, this is the minimum amount of data that would fall within k standard deviations of the mean. Okay, so it could be 75% of the data, but it can be more than 75% of the data. There has to be at least 88.88% of the data fall within 3 standard deviations, but it can be more than 88.88%. Okay, and so on and so forth. So what I'm going to do is I just want to illustrate that this data set, which is clearly not symmetric in any way, it's just a skewed right data set. I want to show how that falls into this category. So what we're going to do is we're going to find a lower and upper bound for 1 standard deviation away from the mean, 2, 3, 4, so on and so forth. So to find the interval that's 1 standard deviation away from the mean, I'm going to take the mean. If you use function 4, you can lock the reference to that mean, and I'm going to subtract 1 standard deviation from that mean, and that's the lower bound of 1 standard deviation below the mean would be at 0.349. 1 standard deviation above the mean would be if I take this cell and I add 1 standard deviation instead of subtract. Okay, so this is an interval that's 1 standard deviation away from the mean, 1 standard deviation below the mean, 1 standard deviation above the mean, and I can figure out exactly how many data points are in between this using a function called countifs. Okay, so the countifs function takes at least 2 arguments. We're going to do 4 arguments. The first thing is the data I want to look at. So I want to look in column A, comma, that's how you separate your inputs here. So those are the different arguments. Arguments are separated by a comma. So now it says find criteria 1. So my criteria is going to be in quotes. I'm looking for all the data in data set A that are greater than or equal to, end quotes, and, so that's shift 7, this value. So what I just wrote there in very cumbersome, not intuitive syntax is look through the data that's the number of siblings and find all the ones that are bigger than 0.349. But simultaneously, we want to find in the same data set A all the values that are also less than or equal to 3.09. So I'm looking for all of the values in my original data set that are bigger than 0.349 but smaller than 3.09, including those values. But since siblings is a discrete value, they're either 0, 1, 2, 3, 4, they have to be whole number values. This is really saying find all the siblings between 1 and 3. So how many people have siblings between 1 and 3 siblings? That's what this is going to find. And there's 38 people. Now I asked, 50 people were asked, so we're going to take this previous number and divide it by 50, and that's the proportion of people in this data set that have siblings that fall within 1 standard deviation. In this case, 76%. So 76% is already bigger than the 75% that Tchebychev guarantees for 2 standard deviations away. Tchebychev does not indicate how much data should be within 1 standard deviation. All right, now if I want to find this for the rest of this data set, it's as simple as copying these formulas down. So I'm going to copy these down, and right now they're not going to make sense, but I'm just going to come into these formulas, this formula here, and I'm going to change the 1 to a 2. And then I'm going to come here, I'm going to change the 1 to a 3, because it's 3 standard deviations below. And then change it to 4 standard deviations below. And over here, 2 standard deviations above. 3 standard deviations above. and 4 standard deviations above. And what we see is that Tchebychev guaranteed at least 75% of the data be within 2 standard deviations. We actually got 94%. Tchebychev guaranteed that at least 89% of our data was going to be within 3 standard deviations. Our data set actually had 98% of the data within 3 standard deviations. Tchebychev guaranteed 93.75% of our data was within 4 standard deviations, and 100% of our data was actually within 4 standard deviations. We will do another problem in a couple videos away from now where we are asked a question about Tchebychev's theorem only given the mean and the standard deviation, and we'll talk more about how Tchebychev works in a regular problem. But for now, just realize that for this data distribution, we were able to talk about the percentage of data that fall within certain standard deviations away from the mean. Standard deviation is an important number. In an even later video, we'll talk about how, in this case, we probably don't want to use the mean to describe the center of our data set because it's skewed right, and we would use the median. And if we're using the median, we don't want to use the standard deviation as our measure of spread, so we will talk about another measure of spread that we can use. I'll see you in the next video.